All right, looks like we have quite a few participants in here already, so we're going to go ahead and get started. We have a really packed agenda today. Welcome and hello, everyone. Thank you for joining us on our Clearing the Air on Carbon Capture and Storage webinar. We have a lot packed into the hour, so without further ado, my name is Eliza Sheff, and I'm the Program Manager at Clean Air Task Force for the Carbon Capture and the Hydrogen programs, and I'll be facilitating our webinar today. For those of you who are not familiar with Clean Air Task Force, we are a global nonprofit organization with more than 25 years of internationally recognized experience and expertise on climate policy. CHF is one of the few environmental organizations in the world that's taking a broad and pragmatic approach to managing climate change by pushing low carbon technology options. Today, we're going to be discussing a science-based perspective on CCS technologies and projects and address common questions that we often see in the discourse around CCS. The webinar is going to feature presentations from our speakers and wrap up with a panel Q&A session. And before we get started, there are just like a couple of housekeeping items that I want to go over with everyone. I do want to remind everyone that the webinar is being recorded, and we will make the recording available to all registered attendees afterwards. Throughout the duration of the webinar, please add your questions to the Q&A box at the bottom as they come up, even while presenters are going and doing their presentations. And then we're going to go through all of them at the end during the Q&A. I'm going to read them out loud in the last 15 minutes. Please feel free to direct your questions towards a specific speaker or just towards the group. My colleague, Cody Rossi, is going to be monitoring the chat and may chime in every once in a while with some resources. Our speakers today are going to be Toby Lockwood, CATF's Director of Technology and Markets on our Carbon Capture Europe team. He's going to start off by focusing on why we need CCS and our current project landscape. Following him, we will have Professor Sam Kreber from Imperial College London's Department of Earth Science and Engineering, who's going to focus on the science behind CO2 storage. Our third speaker is Professor Mathieu Lucchio from Sheffield's University School of Mechanical, Aerospace, and Civil Engineering, and he's going to cover CO2 capture technology. And our final speaker is Professor Andrea Ramirez from Delft University of Technology and the Department of Chemical Engineering, and she will provide a systems perspective on the role of CCS. All right, Toby, you're up.
Thanks very much, Eliza. Hello, everyone, and thanks for joining. So I'll leave as much time as possible for the experts we have on the panel today, but I'm going to briefly introduce the topic and highlight some of CATF's recent work in this field. Firstly, what is carbon capture and storage? We're talking about a set of technologies which put together can provide a solution for eliminating the CO2 produced by fossil fuels or other sources of fossil CO2, such as limestone. The term capture describes the process of separating CO2 from any other gases it's mixed with. In many cases, this is simply nitrogen from the air. The relatively pure CO2 is then compressed to a liquid-like state and transported to a suitable location for storage. This is usually by pipeline, but could be by ship, train, or even trucks. At the storage location, the compressed CO2 is injected deep underground into porous rocks such as sandstones. And we're going to hear more about each of these steps from the other speakers. Next slide, please. So why is there so much interest in CCS? Again, we're going to hear more about this later, but here are two sets of analysis of the action society needs to take to prevent the worst effects of climate change. The International Energy Agency's global net zero by 2050 scenario on the left shows around 6 billion tons of CO2 stored annually by 2050. On the right, an analysis of the many 1.5 degree compatible scenarios looked at in the most recent IPCC assessment report, which highlights the key role played by geological storage of CO2 across nearly all scenarios. This is shown by the blue shaded area at the bottom. We can't predict the future, and we don't know exactly what the optimum global pathway for climate change mitigation will be. But the headline from these plots is that we are overwhelmingly likely to need to store billions of tons of CO2 if we're to have any hope of success. This is why CATF is so interested in helping this technology to develop. Next slide, please, Eliza. So how is CCS actually used in these mitigation pathways? A key focus is in decarbonising heavy industries, such as cement, steel, and chemicals, which really contribute a staggering proportion of our CO2 emissions today, and often have few or no other abatement options available. The storage of CO2 may also be needed for other purposes, such as producing low-carbon fuels, decarbonising power plants, and probably most importantly, the net removal of CO2 from the atmosphere. Next slide. We often hear about CCS as a new technology, but the three component technologies I just described are actually very widespread already. People have been separating CO2 from other gases for nearly a century, either because it's an undesirable contaminant in some products or because we need the CO2 for the food and drink industry. The amount of CO2 being separated commercially is in the hundreds of millions of tons a year. In the USA, CO2 is big business. It's used to improve oil well production. Now, most of the CO2 used for that purpose is actually mined from natural reservoirs, which is of no benefit to emissions mitigation. But the point is we know how to transport and inject CO2 on very large scales. Next slide. If that's the case, then why do we usually hear about just a few commercial CCS projects? Well, these projects often simply represent locations where the availability of already captured CO2 has happened to coincide with a local demand for CO2, usually to boost oil production. These projects are often not aimed at decarbonisation at all, but they have nevertheless reduced emissions and helped develop technologies. On the other hand, there are a growing number of large projects which do store CO2 in other kinds of deep rock formation purely for the purpose of emission reduction. These projects can only be driven by climate policy, whether that be a carbon price, a subsidy, or some kind of mandate. In our report released last year, CATF took a look at 13 of these more integrated projects to assess their underlying motivations and their technical performance over time. Next slide. I'm going to very briefly present a couple of the projects we looked at, starting with Equinor's famous Sleipner project in the Norwegian North Sea. Sleipner was the first project globally to store CO2 for emissions abatement. It was driven by Norway's carbon tax, which disincentivized the usual venting of CO2 separated from natural gas. In recent years, it has stored much less than its design capacity, simply because less gas is produced. The project has occasionally met with allegations that the CO2 has leaked or behaved in an unexpected or concerning way. But these have no basis in the extensive scientific literature on the site. We can't predict exactly how CO2 will move underground, but it remains well within the originally predicted area, and importantly, beneath the geological seal. Next slide. So you might say separating CO2 from natural gas is easy, we know how to do that. What about other sources? It's true that some projects dealing with dirtier gas streams have had to deal with more technical challenges on the capture side. The Boundary Dam coal plant in Canada is a case in point, where CCS has been operating since 2014, but has experienced various technical challenges. It's important to note that the proportion of CO2 removed from the treated coal plant flue gas of this plant is consistently around 90%. However, there are shortfalls associated with less flue gas being treated or equipment breakages. This is a particularly challenging emitter as the gases entering the CO2 separation unit turned out to be far too dirty. However, this has been progressively addressed by better gas cleaning measures and a range of other improvements to the plant. Availability of the process has averaged at 86% since this data set was taken. This is why we do still need to innovate and learn as CCS is used in new environments, and that's what technology demonstrations like this are for. Next slide, my last slide. I'm just going to leave you with these key points. So the large CCS projects we tend to hear about are often not developed with emissions reduction in mind, and they generally have no incentive to maximize the CO2 they store. The few projects we do have today that are motivated by adequate climate-based regulations or incentives have generally performed well. There are undoubtedly projects which have encountered technical challenges, but most can point to an improving trend as solutions to these problems are developed. That said, data availability on many of these projects is sparse or poor quality. We do need clear and transparent reporting of performance. CCS projects being developed today are driven by climate policy rather than commercial drivers and should be under much greater incentive to maximize their abatement potential. And I'm going to leave that little introduction there and pass over to Professor Kreber, who's going to talk about focus on geological storage. Thank you.
Okay, great. Well, thanks very much. Let's go to the next slide. There's a kind of font issue. I hope it doesn't become too much of an issue throughout the slides. So I'm going to be talking about CCS through the lens of subsurface carbon dioxide storage. I'm showing here a graph of the high-level motivation for CCS, similar to one of the slides that Toby just showed, but through the lens of, again, subsurface carbon dioxide storage. And what we're looking at on the right-hand side of this graph are projections of how much carbon dioxide storage might be useful in a given year to meet climate change mitigation targets, limiting global warming to less than 2 degrees C. And these were synthesized, compiled, and summarized by the IPCC assessment report, the most recent report. And what you see on the very right-hand side is a bar which shows that the IPCC report identifies that between 1 and 30 gigatons of CO2 storage per year in 2050 could be very helpful in a technological pathway to allow us to avoid dangerous climate change. And these are very large numbers. To put that in context, a gigaton per year is already approaching the scale of fluids handling that the current oil and gas industry has today. So the lower end of that range, the upper end of that range, 30 gigatons, is starting to approach the current total global emissions. That's also a large figure. And it's reasonable to look at that and ask, is this feasible? Can we really achieve that? And I highlight here on the left-hand side of this graph, actually what we're going to start with now, which is, well, to answer that question, we first need to start with where we are today. So let's go to the next slide. And this information is not compiled centrally and reported and summarized in a kind of simple measure, but actually what you discover is that most operating projects do publicly report how much carbon dioxide has been captured and stored. I'm showing here a time series from 2 projects in offshore Norway, the Sleipner project that was already described, and the Snøhvit project. And you can find this information. There's usually reported with a high degree of assurance from independent auditors, reported in annual statements or sustainability reports from companies. And if you compile all of this information, we go to the next slide. What you find is that a fairly large amount of carbon dioxide has been stored since 1996, when the Sleipner project began. You can find verified and audited or independently assured information of over 200 million tons of carbon dioxide stored from around 20 commercial scale projects. This is just the time series of that. So if we go to the next slide, I get a lot of, I hear a lot from time to time about how CCS is in its early stages, or it's unproven, or in this, with regard to this particular information, that not enough is happening compared to the gigatons that we need to mitigate climate change. And it's true. And there's 30 million tons of CO2 is being stored, and that's very small compared to the 1,000 million tons or 30,000 million tons that may be needed or by 2050. But that's not the fair comparison. And the benchmark that we should really be looking at is what is the mitigation being provided by CO2 storage compared to other decarbonization technologies today? And when you make that comparison, you look at 30 million tons of CO2 stored in 2019, it emerges a much more positive picture. That is essentially the mitigation provided from solar photovoltaic in the United States in the same year. So CO2 storage is early days by some measures, but each of those projects provides a very large amount of mitigation. And in terms of how much carbon dioxide is being mitigated by CO2 storage even today, it's already pushed itself into the league of major decarbonization technologies. So that places it in position to play an important role over the coming decades, and especially by mid-century. So a next question that often arises is if the mitigation that we'll need is possible from the geological standpoint. Is there enough pore space available in the subsurface? This is a question that has been studied for quite a long time, really from the beginning of the idea in the mid-1990s of CO2 storage. And these estimates are robust. The answer is yes. There are between 10 and 30,000 gigatons of worth of pore space, what is now referred to in the technical parlance as CO2 storage resource, available around the world. And that is a compilation of numbers from locations where that has been assessed. There are a number of notable locations, the Middle East, South America, Sub-Saharan Africa, where those numbers are very low right now, simply because there aren't a large number of assessments. So the total space available for carbon storage, the total resource, is abundant compared to what we need. But another question, which is just as important, is how quickly can we use or access that resource? Let's go to the next slide. And this is really a focus of, brings us very firmly into the realm of geoscience and engineering. I'm showing a schematic here of carbon storage in various forms. Carbon dioxide injected to depths of greater than 1 kilometer in the subsurface into various geological strata, oil reservoirs associated with enhanced oil recovery, or domes, or traps up against fault seals, or even in locations where the migration, the movement of the carbon dioxide is optimized to spread out the carbon dioxide so it's trapped within the reservoir through capillary forces, similar to how water can be trapped in a sponge. These are the kinds of things that need to happen to get the carbon dioxide underground. So this schematic not only shows what needs to happen, but it actually shows all of the geological environments in which carbon storage is happening today. So coming back to this issue of whether or not CCS is demonstrated, again, from the perspective of the subsurface, a large number of projects being demonstrated in a wide variety of geological settings with a wide variety of fluid migration, trapping mechanisms, and other technologies associated with that. So if we go to the next slide, get into some of the specific geoscience and engineering issues. Once you inject carbon dioxide underground, it's a buoyant fluid, it's less dense than water, and it will migrate upwards and spread out, and sometimes reacts chemically with the rock and dissolve into the water. One of the main concerns that people have, and certainly the public, is around the risk of CO2 leakage. So it's important to point out that there are no examples of carbon dioxide leaking to the surface at operating projects. There are also, the risk of leakage is also a major concern among project operators. It's widely considered that the largest risk of leakage is for that to happen along old wells that have been injected into the subsurface looking for oil and gas or producing oil and gas and so on. But one of the things that is important to know is that leaks along wells can be mitigated. And this is a mature technology. And so largely in the province of risk assessment in project development, leaks along these wells are a financial and liability issue, less than a technical issue. So go to the next slide. There are also concerns about pressurizing the subsurface with all of the carbon dioxide. And too much pressure can result in seismic activity, induced seismicity, felt earthquakes if too much takes place, and so this is also of great interest to the industry and academic communities. At the moment, again, there are no examples of this at operating projects, and there's a wide consensus that there are an abundance of formations where this risk is really low. So it's not really a near-term barrier to scaling up, but it's an important thing that we're looking at in the context of the gigaton scale of carbon storage. So if we go to the next slide, and I'm going to have to actually move through this. This is to just impress that we have a large number of sophisticated models to characterize reservoirs, to forecast plume movement and reservoir pressurization in the subsurface. One of the things that's happening now is we are employing those models in the service of analyzing the rate at which we can scale up globally. So we're applying these models not just to sites, but locations around the world. And if we go to the next slide, and actually I'm going to skip ahead. So if we go to the next slide, and the next slide, and finally the next slide, this is just to say we've applied those around the world. And some of the outcomes are already emerging as important and interesting, is when we look at scale-up potential in the context of what we know about the subsurface, both the physics and what has been achieved historically, we can say that this range of 1 to 30 gigatons is really should be, by 2050, really should be narrowed down to something less than 5 to 6 gigatons. That's a kind of feasible upper limit of deployment by 2050. If we look at growth right now in CCS, we're looking at getting to around a gigaton per year by 2050. All of these are commensurate with a number of mitigation pathways, still limiting global warming to less than 2 degrees C. And while the numbers are smaller, they really should be thought of as increasing the certainty of what we can achieve. And so I'll go to the next slide. These are just my conclusions. We can come back to that as needed. I think I've used up all my time, so let's go on to the next.
Thanks so much, Sam. All right, and our next speaker is Professor Mathieu Lucio.
Okay, thank you and welcome. Yeah, thank you, Sam, and thank you, Clean Air Task Force, for inviting me. I'm going to talk about carbon capture and storage, what's its value, talk about cost, and then we're going to talk about deployment. Next slide, please. What I'm going to do, I'm going to address 3 misconceptions. So the first, misconception that I often see, when people discuss CCS. So the first one is we don't need CCS. Next slide. So here are 2 examples of things that, as society, we no longer accept. We no longer accept sewage going directly into our river. We no longer accept plastic waste or any waste going into the environment. Next slide. And effectively, what we've developed systems to manage our waste, and we've developed systems to manage our wastewater, and these have become public good infrastructure that we use to protect the environment. Next slide. So, what's the role of CCS, right? And effectively, CCS, when deployed, will become a public good infrastructure that protects the atmosphere against an excess of carbon dioxide, against climate change. So that's the value of CCS to our society today. Next slide. So I've been in this field for nearly 20 years, and I've seen various waves and tranches of CCS deployment. Sorry, can you go back one? CCS always rises from the ashes of previous failed attempts at large-scale deployments. There's been several attempts in Europe, and we finally getting on with the technology. So if you're a proponent of CCS, you can see CCS as the phoenix that rises from the ashes and comes back, or if you're an opponent, you can see as an old chewing gum that you can't get rid of, and it keeps coming back. So let's go to the next slide. So why does CCS keep coming back? Well, it's very simple. The climate drivers for deploying CCS are very strong. Previous failed attempt at deploying CCS do not change the climate drivers, and the value of CCS society is much higher than its costs. Next slide, please. So yeah, so here what I have is pathways from the IPCC that are consistent with a 1.5 degrees of climate change, and on the vertical axis you have a global net CO2 emissions, and the horizontal axis goes from 2010 to 2100. And what's important to see here is that we need to decarbonize. We will need CCS to get to net zero by 2050. But if you look what happens after 2050, we see that for decades we will need to have a sustained effort of effectively negative emissions. We will have to remove excess carbon dioxide from the atmosphere. So the role of CCS is 2 ways. I think Toby's already touched on that. We need to go after our conventional industries, decarbonize them, and we want to remove excess CO2 from the atmosphere for decades at the gigaton scale. Next slide, please. So effectively, net zero by 2050 is only an interim target, and then the long-term target for climate change mitigation is net negative. And if we fail to plan for net negative, we are planning to fail. So we shouldn't focus on net zero. We should focus on net negative. Once you understand that, it becomes clear that it's unsafe or unwise to remove options from the table now, and we need to deploy some CCS now. Future generation will have to pay off our carbon debt to the atmosphere. and they will use their legacy infrastructure that we leave them. They will leave the legacy CCS networks and storage capacity and capture facilities that we leave them. And we are going to build those in the 2020s and the 2030s. And they will also use atmospheric CO2 removal technologies. So we need to leave them these technology so that they can then ramp them up at large scale and they can use them for decades. Next slide, please. So a second misconception, CCS is too expensive. So let's address that. Next slide, please. So what we have here is effectively a comparison between solar photovoltaic and CCS. So on the left-hand side, you have solar photovoltaic. I'll call it the poster boy. And the graph shows two things. It shows the capex for installing solar PV, and it shows the capacity that's been installed over a period of 9 years from 2009 to 2018. So the light blue line on the left show you the capacity going from just under 50 gigawatt to under 500 gigawatts. So in a period of 9 years, we multiply the capacity by 10. And if you look at the cost, they've basically been divided by 3.5, from $2,200 per kilowatt to about $600 per kilowatt. And effectively, we need to do the same with CCS now. So on the right-hand side, you have CCS, which has been the ugly duckling in terms of climate change mitigation. And the diagram compares the investment in solar PV with CCS. So the light blue line is solar PV, and the scale goes from 0 to $80 billion per year. So you see that the investment is basically ramped up from about 20 to 70 billion dollars per year from 2009 to 2017. And over the same period, you look at CCS, that's the vertical axis on the left. The scale has had to be compressed. It's been to 0 and 20 billion $20 billion per year. And we've basically been investing between 0, 1, less than $2 billion per year in CCS. So what we need to do now, we need to invest 10, 20, 30, up to 70, 100 billions of dollars every year in CCS to basically go through that curve and cut the cost by, guess the number, but we need to significantly reduce the cost. Next slide, please. So is CCS really that expensive? Can I have the next slide? What we have here is basically a diagram that shows the cost per ton of CO2 sequestered. So it includes method nature-based for carbon capture, and it includes conventional CCS technology and CO2 removal. And what you see is that there's a range of cost and there's a range of potential. Can I have the next slide, please? Now, what we're looking at carbon abatement cost. Okay, so we're looking at comparing the cost of CCS. So this is the blue line. And then the red line is what's called the conservation abatement curve. So this is all sort of technologies. This is energy efficiency, electrification, fuel switching, renewables, better agricultural practice, et cetera, et cetera. And at some point, what you find is that when you try to go for the last 15% of our emissions, the red curve shoots up. These emissions are really expensive to decarbonize with methods that basically don't include CCS. So if you think like an economist, if you think about going all the way to abating all our CO2 emissions, CCS is actually a cheap way to tackle the expensive to abate sectors, those 15, 20% emissions that we can't abate without any other methods. Next slide, please. And that brings me to my third misconception. CCS is an unproven technology. Next slide. So I've basically here taken a list from the Global CCS Institute showing the many projects that are in operation today. Next slide. There's a second page. So next slide. We have about 50 CCS projects in operation today. What's important to point out is that 15% of these projects are climate projects where CO2 is stored geologically. They're driven by climate change purposes. And then 35 of these projects are effectively enhanced oil recovery projects where the climate benefits are less clear. But nonetheless, they demonstrate that we can capture, transport, and inject CO2 in the subsurface. We have bankable CCS project where there are many projects in operation in a range of sectors: hydrogen, ammonia, fertilizers, natural gas sweetening, and coal power generation since 2015. Next slide. And I've got another table showing you all the projects in construction as of 2024. Next slide. So you see there's a long list again. Next slide. So CCS is not proven in some sectors, some key sectors. So it's not proven yet, but we are on the verge of proving CCS in these sectors. So this includes the cement sector, possibly the steel sector. I put it as unclear because that's for me, some of the projects out there cannot necessarily be replicated to our existing assets. Gas power generation in the UK 2028, biomass power generation BECCS in Denmark, Sweden 2026, and direct air capture 2025 in the USA. Next slide. So to conclude, we are at the crossroad with CCS. We have new projects coming in new sectors, and they must succeed to create confidence with the public, policymakers, and investors. Failures or delays in this project will cause further delays in deployment, but CCS, I believe, will come back again because the climate drivers don't change. And now our role as academic researcher, people in the CCS industry, is to make CCS fit for purpose for net zero and for post-net zero. And that's what the challenges that are basically in front of us in the next 5 to 10 years is eliminate all the residual emissions from CCS, implement best practice in natural gas supply chains so that we can have best-in-class CCS when we use natural gas in CCS project, and then deploy these atmospheric CO2 removal technologies, BECCS and DACCS at the million-ton scale. And I think that's it. Thank you very much.
Thank you so much, Mathieu. And we'll have our final presenter, Professor Andrea Ramirez, if you're ready.
Yeah, thank you. Let's see whether I can do some value added to already nice presentations of my colleagues. So just gonna look a little bit at the system perspectives in costs and emissions next. And the first thing I want to point out is that, of course, we have been speaking about CCS as an option for coal or as an option for natural gas. But actually, if you just take that we want to have CO2 taken out of flue gases, it is a multi-purpose mitigation option. So we are looking at CCS, and that's what we are looking in IPCC. That's also what is International Energy Agency is showing is CCS having a role, yes, to decarbonize electricity, but electricity, of course, can be decarbonized in other means. But you also have CCS for decarbonized industry, especially industry where CO2 comes from the process, like in cement, or where the CO2 is actually quite pure, like if you are producing ammonia. We also have CCS playing a role in supplying hydrogen, and we see a whole movement of hydrogen economy, hydrogen as a way of supplying heat to high temperature industry, for mobility, for aviation fuels, not as the only aviation, but as part for the chemical industry. So if you're going to supply what we call a low carbon hydrogen, then yes, you can have hydrogen from water electrolysis, but that won't be enough, and that won't be enough fast enough. So what we are looking at in all the models is actually portfolio of technologies where part of the hydrogen, that low carbon footprint hydrogen, is coming from fossil fuel chains or from bio chains where carbon capture and storage is implemented. And the last one is the last point that Mathieu was doing is carbon capture and storage having a big role on negative emissions. Next. So I realized that Matthew's presentation was cost, and he spoke about systems, and my systems, I'm going to speak about cost, but they are highly interrelated. And what we show here is from the Global CCS Institute, but we just see similar pictures in many publications, and it's how much does actually capturing CO2 from a flue gas cost. And on the left, you will have in gray all the what is in fossil fuels, so power plants there. And in the right, you have the actually industrial sector. And you see a large diversity. We see values between, most values between 50 and 150 euros a ton of CO2. And you see also, relatively large bars. And that is because when we look at the cost, especially in the industrial sector, you need to look at the location where CCS is implemented. So is it implemented in a place where you have excess heat available, waste heat available? It's in a place where actually there is none, and you have to install a boiler, a CHP, or you have to have a solar power, or you have a bioenergy source. how is the pipe, and what is the concentration of the CO2. So all that makes that the cost that people read in literature is actually are quite different. The second point, and people keep saying, yeah, well, you get, or we get the cost wrong. When you build a house, just a normal house, you only know how much the house costs when you build it. It's a little bit similar here. We are only going to know the real cost of some of these projects when we build it, but we have a pretty good idea of where they are and the order of magnitude where they are. Next. So now when you look from a system point of view, you can focus on the plan where it's implemented. That's an important part. Somebody's going to implement it, and that is going to have an impact, for instance, in the price of the product, whether it's the price of electricity, or whether it's the price of cement, or the price of steel, or the price of ammonia, or the price of a fertilizer. But in reality, in society, we don't want electricity for the sake of electricity. What we really want is lightning. What we really want is heat in our houses. What we really want is a bridge, a hospital, a house. We want to actually move from A to B. So that's also why we have a fuel. So if you look at it from a service point of view, then you get a slightly different picture on how expensive carbon capture and storage is. So what we have done in this is, and we are not the only group doing this, and this was work done with Sintef in Norway, is how much will it cost if we look from a service point of view, and we took a bridge. Next, just because we want to have infrastructure. Infrastructure is something that around the world is going to happen a lot, either because we have old infrastructure that needs to be replaced, or because developing countries or global south actually has to be still a lot of infrastructure. And we took a case study. Actually, we take the Guinness record holder for longest bridge over water. And if you don't know where it is, it's actually in the US. It's called the Lake Pontchartrain Causeway. It's 39 kilometers long. And we say, okay, this bridge, you need several things, but two main components for this kind of structural work is concrete, for which you need cement, and it's steel. So if that concrete and that steel would have had CCS, what will be the emissions of this bridge, and how much will the cost have increased for the final user? Because we as taxpayers, we pay for this kind of constructions. Next. So that's basically what we did. So we have there in the middle, we have the bridge, and we say, well, how much concrete actually this bridge need, and we calculated or estimated around 225,000 cubic meters of concrete. And in concrete is, the bags you buy in the supermarket, and if you look at that, a part of that, but not all the bag is cement. So actually concrete is composed of cement, and it has sand, it has aggregates, you have to put water, you have to put additives, and that's what you do actually to have the material for which we use in today's daily life. So yes, we need 225,000 square meters of concrete, but that means we need around 76,000 tons of cement. And you will do the same with the steel, and we have around 25,000 tons of steel only for the bridge. And let's now imagine that at the beginning of the chain, where we have the steel production and the cement production, we have put a carbon capture and storage unit there. Next. So when you put cement and you put carbon capture and storage, and we just take one of these values and did the analysis, the cost of cement, of your bag of cement, not concrete, cement, increased around 80%. But your carbon footprint reduced by 90%. And I'm just speaking about the carbon footprint only in the factory, but this is actually a life cycle assessment to the gate of the cement. So all the upstream, the mining of the lime, the transport of material, that is including that carbon footprint. If you look at the steel plant, the cost of steel that we will need for that bridge increased by 13%, and the emissions decreased by 47%. Now, when you put those costs and you look at the bridge, what we found is actually the cost of the bridge itself was increasing only by 1%. But the emissions of the bridge decreased by 51%. So the original bridge, we calculate costs around, because it emits around 130,000 tons of CO2. And if you would have had CCS in the iron and CCS in the steel plant, you would have decreased that to 64. It's not zero, but for a 1% increase in price, it's actually a significant reduction in emissions. Next. And we then say, okay, but maybe this is very specific for, you know, this kind of a structure with a lot of steel, a lot of cement. What happens if we take something else? So we have taken 10 case studies. We have looked at what about avocado, where you need fertilizers, and for the fertilizers you will need urea, and for the urea you will need ammonia, and in ammonia you actually can put carbon capture and storage. What about a book? And you will put carbon capture and storage in the pulp mill. What about, you know, a wheat mill, which actually needs a steel, and we will have CCS in the steel. And we did it with a lot of cases, and you see also the bridge case there. And we look from an LCA point of view, but also from a cost point of view, what will be the trade-offs. Next. And what you see there, and you see a long kind of bar, with black and with orange or with green, which has a little bit of stripes, that is your emission reduction in percentage after applying CCS in upstream in the upstream materials. And what you see in the low kind of bar that say 1% or 2% or I think 10%, when you have it in waste treatment, that's basically putting CCS in an incinerator. That second bar is the increasing cost for the service. So whether it's for the book or for the avocado that you have and you buy in the supermarket, or you know, for the fertilizer that you buy. The only place where you see a high increase in the price was in air travel. And air travel was a specific case study we look at, and it's not that you are going to put a carbon capture and storage in the plane. That was not what we tried, but we put actually direct air capture to compensate for the emissions. And then if you pass the cost to the consumer, the price of the plane tickets would, you know, increased by 80%. For all the other cases, it was around, you know, 1 or 2%. Next. So the other thing, and in my work, we combine a lot of techno-economic analysis with life cycle analysis, a lot of discussion about the real, you know, mitigation option and the comparison of carbon footprints. And this is something that was published by International Energy Agency, and we have got, you know, you can find this kind of picture. It's generally what you see when you look in the literature. And these are carbon footprints to produce hydrogen from different kind of sources. And if you look at the coal and natural gas and electrolyzers, of course, electrolyzers has the lowest. The only one that actually gives you a negative one is biomass with carbon capture and storage to produce hydrogen. So the biomass trees have carbon, but also have hydrogen, and you can take the hydrogen out from there and store the CO2. And you also can do hydrogen as we do it today, which is called gray, but put a carbon capture and storage and then decrease. So we do see that depending on not whether you have carbon capture and storage, you actually began to get very similar carbon footprints. This has one caveat, and that is in the next slide. And if you look in the next slide, what we are showing is what will be the carbon intensity of hydrogen if you have different electricity carbon intensities of different countries. We did this for Europe, and then you see in the line that it goes a little bit 45 degrees, that are the different countries and the carbon footprint. In the Netherlands at that moment, it was around 600 kilograms CO2 per megawatt hour. And if you will apply the intensity to an electrolyzer to produce just hydrogen from water, but with an electricity that does not have carbon capture and storage, you are going to produce more emissions than what we have today in a normal natural gas plant producing hydrogen without carbon capture and storage. So if you want to be lower, you really, really need a carbon intensity in your electricity mix that is really, really low. In our case, in Europe, for instance, Sweden would reach that, or France that use a lot of nuclear energy. But if you will go into it in the Netherlands without using green electricity, then you are actually creating more emissions while thinking that you are using a very clean source of hydrogen. So that is the caveat. The second caveat, and I'm almost done, is in the next one, and is that, of course, it depends a lot of how is your natural gas footprint. And we see that leakage plays a big role there. Can I have the next slide? And what you see in dark blue, so I know the size is small, and you all guys are gonna receive the, you can see the slides later on, but you see at the blue, and it's really jumping out, those are the emissions that you have from methane leakage. So in order for having something playing a big role, it's not only having the carbon capture and storage in natural gas, for instance, but it's also taking care of the upstream emissions. If we don't take care of upstream emissions and we have a lot of leakage, then the picture and the conclusion completely changes. So it's taking care of the two things. Where is my electricity? Where is the natural gas, for instance, coming from? Where is the electricity coming from? Where is the biomass coming from? And how am I using it? What will give you the carbon footprint? It's not technology that is inherently, sustainable. You will say the electrolyzer is sustainable. Well, yes, if the electricity is clean with a very low carbon footprint. Next. And I think that the next one is my final slide, and we can have the
perfect. Thanks so much, Andrea.
Just this one to say system boundaries matter. And this is, as a life cycle specialist, where I would like to put a lot of emphasis. If you are going to speak about neutrality, if you're going to speak on negativity, you need to have the largest potential system boundaries that you can. So really cradle to grave. Partial system boundaries are useful for decision making, for instance, within a company, but by changing the boundaries of an assessment, you can change your results very, very easy. So that's something to just take care. And I think with that, let's finish and let's go just into the discussion.
Great, thank you so much, everyone. No such thing as a free lunch. I'm going to stop sharing here.
Yes, please.
And it would be great if everyone could just bring their cameras back on so we can go through. We have about 12 minutes for Q&A. Thank you so much to those of you who were in the chat and answering questions. Really appreciate it. Looks like it was very active while I was screen sharing. And thank you for bearing with me with my trigger happy slides. Okay, so we're just going to dive right in. Let's see. There are some really great questions in the chat. I'm going to start with this one that was directed towards Andrea and Mathieu specifically, but anyone can reply. How do industries and hard-to-abate sectors choose between different decarbonization options when CCS is one of them? In other words, do we know how convenient it is to use CCS instead of an alternative abatement technology for a specific industry?
I can start maybe, and then I mean, the very first thing is, if you're a plant, you want to use CCS to decarbonize, do you have access to a transport and storage network to get your CO2 to a storage site? I think that's the very first question. If an existing asset, you need to look at space, and then after that, you can start looking at cost and whether you have access to energy. I think there are industries that we can only decarbonize with CCS, and there are industries where there are a range of options. One option is fuel switching. So you can, if you're using fossil fuel for heat or for in some applications for even your process, you can switch to hydrogen. Then the question, you get into this question that Andrea was alluding to, that what are you decarbonizing by using hydrogen? What's the carbon intensity of your hydrogen? And so it's also important to have I think a holistic view in that sense. So yeah, I mean, it's a difficult question, and it's very site specific, I suppose. So difficult to get.
Yeah, I think it's very site specific. I think it's also the big problem of how do you look at what is the speed of the change you want to do, and how much is going to influence your decision making. So I want to take a decision that is only for 2 years or for 3 years. I'm going to take a decision that is going to be for 5 years or for 10 years. And the reality of industrial cycles is the big investments do not happen every year. happen every 10 years or every 15 years. So at that moment, you're actually locking in for a relatively large period of time. So what are the options? And if you lock in the wrong way, that can be a problem. So, or could be problematic. So things like, what do I need to have in place in order to, for instance, I'm gonna go to hydrogen, but is there enough clean electricity or plants for clean electricity that will allow me to move to hydrogen? If no, okay, then I can move to hydrogen, but then I will also allow blue hydrogen. And blue hydrogen then will be there until I have enough green hydrogen. And then you are start to look in it in terms of portfolio. And I think that's actually how most companies do it. They look in portfolio and look at options that allow them as much freedom as possible because they know the future is uncertain. It's not a perfect answer. Most decisions in the industry and at home are taken under a lot of uncertainty.
Anyone else want to chime in? No worries. If not, we have other questions. Thanks so much for those answers, guys. I'm going to move to another question. This one is specifically for Sam. We are seeing very long development timelines for CO2 storage projects. And you did mention how important the speed of development deployment is for storage projects in your presentation. So what's dictating this slow pace? Is it technical issues, permitting issues, business models, investments, et cetera? And how can we speed up the pace?
Yeah, it's a great question. That, you know, in terms of what is setting the timeline, it really is all of the above. Yeah, I think especially with the in the American case now, we're seeing kind of permitting timelines that are contributing significantly to the development timeline. Financing for large projects is always going to be a significant contributor, and typical timescales of what we call exploration and characterization of sites, also in the creation of injection wells and so on, is always a few years. I think one thing that is of real focus right now are the processes for permitting to see if efficiencies can be gained there. I'd say what's really important, you know, as we look at that, is to maintain the balance of rigor in the, you know, in the development of sites, that we're not cutting corners, because I think resulting in projects that fail by some technical measure or another would be very negative, would have a very negative impact, especially in the early stages of development of CCS. But another thing that will help is, as projects develop further, we get a lot of experience. We can make use of geological analogs from past projects and so on. So that will also contribute quite a lot to the development timescales, especially on the exploration and characterization side. And on top of that, as organizations are building up a portfolio of sites, they'll have some sites that are, you know, all but shovel ready, so to speak, for the time when the right policy and business environment comes around. So that will also help.
Thanks so much, Sam. Move on to another question. Toby, I'm going to direct this one to you, but also, again, anyone can chime in here. From a political and policy perspective, how can we make sure deployment of CCS does not incentivize continued fossil fuels exploitation? This is a question that we get a lot at CATF, and I'm sure the rest of you get the same.
Yeah, thanks for those. I think it's, you know, first of all, important to emphasize that the primary challenge facing society is reducing emissions. So that needs to be the focus. I think reducing fossil fuel consumption is also important, and that's clearly going to require regulatory drivers. You know, the carbon price, a strong carbon price, is can play a central role in that. Yeah, I mean, generating electricity or generating energy or materials with decarbonized fossil fuels is unlikely to be the cheapest option going forward. So as we subsidize, continue to support other forms of decarbonized energy and industries, then I think the market will inevitably win out, and the lowest way to achieve decarbonization targets will win out. Happy to have anyone else's thoughts on that.
Yeah, I guess I'll just say that we will run out of space in the atmosphere before we run out of fossil fuels. So and also before we switch away from fossil fuels, we use 80% of global primary energy from fossil fuels, and we only have 25 years to go. So we need to stop the CO2 going into the atmosphere, and then first, and then do whatever we want to do with fossil fuels after that.
If you want my cup of tea, I think
Go for it.
One thing that can be done is actually having clear boundaries and metrics and compare apples and apples with peers and peers, because I do see also in legislation a lot of comparisons that you say, well, are actually comparing. You are comparing removals with avoidance with switching with mitigation, and that is very confusing for people in the field. It's very confusing for people outside the field. So does it incentivize the use of fossil fuels? Then the question is, okay, what are you using fossil fuels, and can we have CCS in a place where that actually start to allow shifting? It has to be allowed shifting. We're keeping still, energy security, while keeping still energy access, and those are a really important part of how do we look at this. So there is a question there that says, isn't the renewable energy a better option? Well, better in terms maybe of emissions, and I think over time we are moving there. But the question is, how do you manage this at system level when you don't only want clean energy, but you also want reliable energy and accessible energy? And if you are only dependent on one type too early before the system is prepared for it, then you are going to have issues with reliability. Then you have to have a lot of storage, and a lot of storage require materials, and then you start to complete the system. So I'm not saying renewable energy is the way to go. It's the way to go, but how do you reach there in a way that society can actually move with you and move faster with you? And I don't see, and that will be my final message, I think pitching solutions against each other, which we have been doing for a while, A against B, CCS against biomass against wind against nuclear. That all the models, we look at them and we need portfolio of options. We need options. What works in the US may not work in Africa. What works in Colombia doesn't work in the Netherlands, because the location, the availability of resources, the capital that you have is just different. So we need to have options that allow us to reach there in different ways. And pitching each other just in a black and white, I think that is now coming back in a status quo where we don't move forward. So looking at how to build synergies and what works in different locations, I think that will help to find a place for CCS, as well to find a place for other mitigation technologies.
Thank you so much. That was honestly such a great answer for us to end on. We are unfortunately at time. I feel like that Q&A session was too short. We definitely could have kept going, but unfortunately, it's all we have time for today. And I just want to take a moment and thank our speakers for their insights and their presentations, and also thank our audience members for their participation in the chat and in the Q&A. We do hope that you guys found today's session valuable and informative. And if you have any further questions or you want more information on the topics we discussed today, please go to the Clean Air Task Force website, or you can reach out to us directly. Thanks so much.